In the earlier classes, we have discussed or found that the motion of the electron around the center of mass is governed by the three quantum numbers, and the wave function describing the relative motion is governed by phi and three quantum numbers n, l, m of r is actually given as psi n, l, m, r theta phi is equal to, apart from some normalization constant, this is the radial wave function. This radial part is a function of rho, and remember that we used rho is equal to alpha. This was the substitution, and alpha n was defined to be h line square 2 into 2 mu epsilon, where epsilon is the energy. The energy was found to be minus epsilon, and this goes as 1 by n square. Epsilon goes as n square. So if this quantity is actually very depends on n and on and writing specifically epsilon n is given by epsilon n is given in terms of the radius and other things as where a mu, the reduced Bohr radius, is given by electron rest mass a0, Bohr radius electron rest mass m0 by mu. If we assume that the nucleus to be infinitely heavy, so that the center of mass lies with the nucleus, in that case a mu is equal to a0, and a0 is Bohr radius. So the point that, and the value of a0 is 5.29 into 10 to the power 11 meter. The point that I was trying to make out, that rho r is a function of rho, so it is basically a function rho is equal to r by alpha n. So if we write y alpha n, so this is twice z r by n mu. So and this part, angular part, is the theta phi part. If we write it in terms of associated log polynomial, then this part becomes normalization constant. Then we will have r to the power l, r to the power l, l n plus l, 2l plus 1 of 2zr n mu e to the power minus rho by 2. Recall that e to the power rho by 2. So this becomes e to the power zr by n mu, and then y element part there is Plm of cos theta times e to the power Im phi. So this is the wave function that we obtained. Now we see that the relative motion is governed by three quantum numbers. This n quantum number is related to the energy. It has energy. It is related to energy and size of the orbit. The larger the value of n, larger is the orbit. Then L quantum number, it determines the shape of the, this is the orbital angular quantum number, which specifies the quantization of orbital angular momentum, and it determines the shape of the orbit. As for example, if L is equal to n minus 1, the orbit is circular. And otherwise, for L not equal to n minus 1, the circuit is, this orbit is elliptical. So L value determines the eccentricity of the orbit, circular orbits. And M quantum number determines the projection of orbital angular momentum quantum number in the direction of the z-axis. So these are the three quantum numbers. Now we come to the probability. We know from our basic knowledge of quantum mechanics that psi star psi is the probability density. So if we write this quantity P n L m of r dv, this gives you modulus square dv, where v in spherical polar coordinate, dv volume element is denoted by So this is the volume between r and r plus dr, theta and theta plus d theta, and phi plus d phi. So this gives you the probability of finding the particle within v around r at around r theta phi when the electron is in a state NLM. But due to this type of behavior of phi angle, this is only has r theta dependence, no phi dependence. That is, if we consider a cylinder whose axis is the z axis, then on the surface of the cylinder, the probability density will be the same. That is, it has cylindrical symmetry. This is the three-dimensional probability density. We can look at the figure, look at the situation in different way. We may first separate out the radial and angular part. That is, we get the total probability density, radial probability density. So we recall once again, this gives you the total probability density, that is the probability of finding the particle or electron within a volume v around r, dv around r, when the electron is in a state this. And we say that the probability density doesn't have any phi dependence. So we derive this as r theta, the Kant called the total probability density. We call it total probability density, total or complete probability density. This part is the probability density. Now we come to radial probability density. We integrate it out over the angular part. So we get psi NLM modulus square r square dr, and this part is d omega. So what we do, we r square dr d omega, we integrate it over the angle, solid angle. We integrate it over. So the resulting quantity that we will have is like this. there will be angular part and radial part. Recall that in this equation the angular part and radial part are normalized separately. So when we apply this, we will have RNL square R from the radial part, square from this side, there is no integration, and then R square dr, and the integration is over omega. It is YLM star of theta phi, and YLM of theta phi integrated over total solid angle, and this quantity is unity. So we are left with R square RNL square of R dr. This is called radial probability density. So we define the radial probability density function as R square. Due to this factor, our DNL at R is equal to 0 is always 0, but as this is a finite quantity always, so DNL of 0 is 0 irrespective of the values of NL. There are two quantities, one is RNL, another one is DNL. They do represent two different quantities. As for example, R1S, that is R10 of R is given by 2 Z by mu to the power 3 by 2 e to the power ZR by mu. This wave function are, if we plot this R1S, it has a maximum at R is equal to 0 and then dies down exponentially. So it is its behavior. But if we go to the corresponding DNL function, it is something different. As I will calculate it, it has a maximum at, this is called A0, or sorry, this is at A mu, has a maxima at A mu and then falls exponentially. I shall consider few low-lying states of hydrogen atom and plot their probability densities. The wave function corresponding to 1s state, n is equal to 1, L is equal to 0, is actually given by this. If we assume Z to be 1 for hydrogen atom, and if we further assume that the nucleus to be infinitely heavy, so that A mu may be replaced by A0, then this can be written as A times e to the power this. And the behavior, this is the behavior of R1s function. It decays exponentially. Similarly, for R2s, it is the wave function general form, and if we assume Z is equal to 1 and A mu, replace A mu by A0, the form is this. This wave function at R is equal to 0 is a positive quantity, and then with the increase of R, this part starts dominating, and the wave function for R greater than twice A0, this is 2. This is the case when R is equal to 2A0, and after for values of R greater than twice A0, the wave function is negative and reaches approaches 0 from the negative side. And for R21, that is R2p, this is the state which can be written as in this form. This wave function is 0, this wave function is 0, at r is equal to 0, and with the increase of r, this part initially starts increasing due to this factor, but for higher values of r, this part starts dominating and the function is this form. These are the radial functions. The corresponding, we shall first consider the corresponding probability densities. d1s of r is equal to r square r1s square of r, which is a square r square e to the power twice r a naught. If we differentiate this and set it equal to 0, dt for its maximum, we write it, first we differentiate this one, a square taken common, so this is twice r, and when we differentiate this one, we get 2 r square a0. If we set it equal to 0, this part is 0 for r is equal to 0 and r is equal to a naught. R is equal to 0 is not a maximum, it is this part, and it is a maximum at r is equal to a0. This is called the first Bohr radius. Now we see that this is the radial wave function and this is the radial probability density. Actually, the radial probability density dNL dNL of R gives you the probability of finding the electron between a spherical cell of radius r to r plus dr, and this is independent of the angular part, as the angular part has already been integrated out. Now coming to the 2s state. The calculation for 2s is slightly involved because it has b square r square and then 1 minus r by twice a naught square, and this part is r by a0. If we differentiate d2s and set equal to 0, so d2 this is the expression. So if we at r, this is 0 for r is equal to 0, which is this point. This may be 0 again at r is equal to 2a0. This is the r is equal to twice a0. So and if we this part, if we set this part is equal to 0, which gives you two values of r, these are the maxima. One is 0.76 and 5.2. basically this is 3 plus minus square root of 5. These are the two values. So this one value is here 0.76 and this is another value. None of these two results matches with the Bohr's theory prediction. Note that this R2s orbit is not a circular orbit. So there is no question of reconciliation with the Bohr's theory. Now coming to D2P state. D2P state is basically c square r to the power 4 e to the power, we use this form, r by a0. If we set it differentiate and set it equal to 0, then we find that d2p dr is equal to c square r cube 4 minus r by a0 e to the power r upon a0. So this is this r is equal to 0 is this point, and this part will be the corresponds to a maxima. It is the 4a0. This is in accordance with Bohr's theory, because Bohr's theory Rn is equal to n square a0 Bohr radius. So for n 2p state n is equal to 2, so it is the maximum probability is at 4a0. Remember that for L is equal to n minus 1, it is the circular orbit, and for this circular orbits Bohr's prediction matches with the quantum mechanical prediction, but for other values of L, the quantum theory will differ from the that of Bohr's theory. Now we again come to this part, and we will look at this situation from a different point of view. We see that the probability, radial probability density are 0 except for few selected values of r. As for example, it is appreciable around, for one state appreciable around 1s a0, for 2p state it is 4a0, and for 2 state it is maximum around 5.7 in units of a naught. This actually defines the stable orbits. That is, if we allow the electron with minimum possible energy, then the most probable electron, it is most likely that the electron will be found in an orbit having r is equal to a naught. Similarly here, it is most likely that the electron in 2s state will be found at this distance, which is the concept of orbits. Now we come to angular probability densities. The total probability density, as we have remarked earlier, depends on 3 quantum numbers n, l, m. So we try to look at the situation in a different way. We first integrated out the radial part, and we looked at the radial probability density. Now if we angular probability, angular probability density P L M, actually it is a function of theta phi d omega. This is y L M star of theta phi, y L M theta phi d omega. This gives you the probability of finding the electron in a state Lm within the solid angle d omega around theta pi. So because of the factor e to the power, recall once again that it is Plm of cos theta times e to the power minus Im phi, and this is e to the power Im phi. So phi dependence goes. Again, as for total probability density, the angular probability density also has cylindrical symmetry. Now we consider few special cases. So basically saying this is PLM cos theta square times d omega. So the angular probability density function PLM of theta, there is no phi dependence, it is basically YLM modular square, which is PLM cos theta square. So for y is P00, that is, it is a constant, this is y00 modular square, and it is 1 upon 4 pi, as y00 is 1 upon square root of 4 pi. Now P10, this is y, this is equal to cos square theta, and P11 this is the function. We see that this part doesn't have any angular dependence. So apart from cylindrical symmetry, it is spherically symmetric too. If we plot it in Cartesian plots, it will be and this value is 1 upon 4 pi. But people generally plots this in polar plots. This is its Cartesian plot. The polar plot, one considers this vertical axis as the z-axis, the vertical axis is the z-axis, and the horizontal axis actually represents the xy plane or the horizontal plane. So the angle theta is measured from z-axis. So if we write this one, this angle is theta, and this part is actually PLM theta. This part is PLM theta. This is the polar plot. So if we plot this, we see that it is same value for all angles of theta. So the corresponding polar plot is a sphere. Now coming to this one, we are considering only this part and leaving apart this numerical factor. So this is the polar plot, this is z-axis, and this is P00 theta. Now this is the z-axis and this is the x1. At theta is equal to 0, this is maximum, this is 1, and as theta increases, it comes to 0 at 90 degree, and then it has a, when we rotate it about phi, we get a curve like this. This is the polar plot of P10. And the polar plot of P11 similarly, it is 0 at theta is equal to 0, and so symmetric. This is P11. Let me first see whether this matches with let me justify this graph analytically or mathematically. That is, if we differentiate this dp10 d theta, this is apart from this part, sin theta cos of 2 theta. This part is 0 at theta is equal to 0 and theta is equal to 90 degrees. So, this is theta is equal to 0 or theta is equal to 90 degree. At theta is equal to 0, cos theta is 1, so it is minus 2, so it corresponds to a maxima. And at theta is equal to 90 degree, it is minus 1, so it is plus, so it corresponds to a minima. And coming to P11, P D2 dP P11 is governed by sine square theta, so this is equal to sine of 2 theta, and when we differentiate it once more, this is 2 cos theta. Again, this is 0 at theta is equal to 0 and 90 degree. At theta is equal to 0, this is a minima. At theta is equal to 0, it is a minima, and at theta is equal to 90 degree, it is a maxima. So, we see that the polar plots can be justified by mathematics. Now, if we look at the polar plots for higher values of L and the corresponding values of M, we see that for M is equal to 0, the plot is all along z axis. For M is equal to 0, M is equal to 0, the curve will have the similar behavior as is apparent from L is equal to 2 and 3 cases, which are available in any standard text. Since M is equal to 0, the projection of orbital angular momentum along the z axis is 0. So, the particle remains confined within xy plane, in xy plane, and since it is orbiting in xy plane, the angular momentum is directed perpendicular to the xy plane, and hence the maximum probability for angular distribution is obtained along z axis. And when we use the value of L is a value of M which is maximum possible 1, that is the particle is or orbiting very close to z axis, very close to z axis, and and the angular momentum vector will be mostly in xy plane. In between, this is the nature for minimum M is equal to 0, and this is for maximum value of M. In between, the curve passes through intermediate steps, as for example, this is the z axis and this is P21 graph. It's symmetric, this is the nature. So, the angular probability density, these are about angular probability densities.